Hello everyone and welcome. Today I'm going to talk about our DAG 19 paper, Embedding Functions into Reversible Circuits, a Probabilistic Approach to the Number of Lines. So first of all, what are reversible circuits and why are we interested in them? Reversible circuits are a kind of circuit that are underlying various emerging technologies, including quantum computing. Formally, reversible circuits are defined as circuits that are built out of individually reversible gates, and a reversible gate is a gate for which the input can be deduced from the output. So for example, a NOT gate is reversible because if we know the output, then we can deduce what the input was. In order to be able to deduce the input from the output, these gates need to be one-to-one transformations, and therefore they always have the same number of input bits as output bits, and therefore also the whole reversible circuit has the same number of input bits as output bits. Therefore we can visualize them like this here, so like a collection of horizontal lines which represent the inputs, and some gates that are placed on these lines. And the way that such a computation is now performed is that we place some input pattern on the left side, and then we move this pattern from left to right, and each time we pass some gate, then this gate is applied to the input. Mathematically, these reversible circuits are simply functions, or they define functions from n bits to n bits. And conversely, there is a result that says that if we have a function from n bits to n bits that is invertible, then we can also build a reversible circuit that computes this function in a certain sense. And the way that it computes this function is that if we place some input pattern here on the left side and we apply this circuit, then the output pattern will coincide with the function f applied to the input on the first n lines. Now, this can be understood as a universality result, but of course this is a very limited universality, because we are asking here, we are requiring the function f to be invertible, and of course many of the functions we may want to compute are not invertible. So if we want to compute a general function, possibly a not invertible function, then we need to use a certain trick, which is described now here. So if f is now an arbitrary function, which we want to compute, which is maybe not invertible, then what we do is we search a larger function which is reversible and which embeds the function f. So f tilde is now this larger embedding function, and embedding means that if we apply f tilde on some input which is x on the first n bits and 0 on the remaining bits, then the output will coincide with the function f on the first m bits and have in the remaining bits some arbitrary values which we don't care about. So these are the so-called garbage bits. And since the number of bits generally corresponds to very expensive physical resources, in quantum computing, for example, this would be the qubits. So therefore, what we want to do is we want to know what is the smallest possible capital N for which such an embedding function exists. And this is what we call the embedding problem. Now, this is in general a hard problem, so it has been shown that this problem is actually NP hard. Yet there is an analytic solution. So this analytic solution is given by a few mathematical identities. So we define the quantity mx as the number of input patterns that are mapped by the function f to the same output as x. So for each input pattern x, we define this subset of the input space as m of x, and then we define the quantity mu as the size of the largest of those sets mx divided by 2 to the n. Now 2 to the n is the number of all possible input patterns, because we are working on an n-bit input space. And so in particular, this will always be a number between 0 and 1, because these sets m of x are a subset of this input space. And finally, if we now define capital N, or if we set capital N equal to n plus m plus the ceiling of the logarithm base 2 of mu, then this capital N happens to be the solution to this embedding problem. So here this n and m are the number of input bits and output bits of the function f that we want to compute. And now n is the smallest possible number of bits for which we can find such a invertible embedding function. However, for general functions, this quantity mu cannot be computed efficiently. So if we want to compute it exactly and deterministically for a general function, we really need to look at all 2 to the n input patterns. So what we propose in this paper is to look probabilistically at this problem. And this probabilistic approach is based mostly on this observation. So this is an observation that these quantities that we defined here can be interpreted in a probabilistic context. So most importantly, this quantity mu can be interpreted as the probability of a randomly chosen input pattern x belonging to a set m of x, so that for this input pattern x, this set m of x is a subset which is maximal, so that it satisfies this property that it's that the proportion of the size of this set among the whole input space is exactly mu. And the probability of a randomly chosen x satisfying this is at least mu, right? So with this starting from this observation, we can now approach the problem as follows. So here we are looking now at a function with 2 output bits, and so with 2 output bits we get 4 possible output patterns, and these output patterns partition the input space into 4 subsets. And this problem is now essentially to find which is the largest of these subsets and estimating how large this subset is. So the approach is now to sample uniformly at random some input pattern, and then continue sampling other input patterns and looking at how many of those are mapped to the same output as this initial input pattern that we sampled. And this gives us an estimate of the set of the size of the set m of x for this particular x that we sampled here. But now we know we have an estimate of the size of the set for one particular x, but we don't know yet that this is really the max. So we need to continue like this with, we need to repeat this process, right? So now that we have estimated the size of the set for one input pattern, we now sample again another input pattern, and here again do the same thing. And we continue like this. We do this for a certain number of input patterns, and for each of these input patterns we sample a certain number of other input patterns to estimate the size of m of x for each of these input patterns x. And then the max of these numbers that we obtain is our estimate. So the main technical contribution of our paper was to do an exact probabilistic analysis of this problem and to find out how many do we really need to sample. And so this is what we did, and we found these expressions here. So S and T are the size of these loops that we have here. So S is the number of input patterns that we sample, and for each of them we sample T other input patterns to estimate the size of m of x for each of these S many x values. And using these sizes, we get certain guarantees that are summarized in this theorem. So this theorem asserts that this algorithm takes as input, or we can provide it with parameters epsilon d and epsilon p, and using for these parameters the size of the loops that we just showed, we get a value, we obtain a value that differs from the correct answer by a quantity of at most epsilon d with a probability of at least 1 minus epsilon p. So with probability arbitrarily close to 1. And the runtime of this algorithm is given by this expression, which may now, first of all, look maybe somewhat confusing, but here really the important thing to notice is that this is the product of two terms. So we have here one part and here another part, and this is the only part that depends on n and m, so on the actual size of the function, and all of this part does not depend on neither n or m, but only on these error probabilities and on the precision of the result. And this ET of f is the average evaluation time of the function f. So in particular, if f is a function that can be computed in polynomial time, then also all of this here is polynomial in the size of the function. Now remember that between this quantity mu and the number capital N that we want to compute, that which is the number of qubits or lines that we need, there was this relation given by the ceiling of the logarithm. And what this implies is that if our estimate for mu falls somewhere here, this red point is, and then if this epsilon d interval around this point looks something like this, so that it does not intersect the point 0.5 or 1, then what this implies is that this estimate of capital N that we would obtain is actually exact with probability epsilon p. And the reason for this is that the ceiling of the logarithm is constant on this interval, and also it's constant on this interval, so between 0.25 and 0.5, and also for higher powers of 1/2. It's always it's constant between consecutive powers of 1/2. And for that reason, our estimate here would be exact. So no matter where exactly in this interval the true value is, it always all leads to the same value of n, and therefore this is exact. If now this interval, however, would intersect a power of 1/2, so in this case it could the true value could be either in this interval, so on the right side between 0.25 and 0.5, or on this left interval, which goes from 0.125 to 0.25, and depending on where the exact true value is, our estimate of n could be off by 1. So that would be the case if we now use this estimate, but the true estimate or the true value of mu would be somewhere here. And likewise, if it now goes even further to the left, this interval can intersect with several of those powers, and in that case the estimate of capital N that we would obtain could be off by more than 1. In this case, if this uncertainty is too big, what we can always do is then to just run the same algorithm again, but with a smaller value of epsilon d, until we get enough confidence, or that's to say an interval that is small enough so that it contains no more lines than we accept as uncertainty. Now, to test our method, we ran it on the Reversible benchmark functions, and we compared it with 3 other existing methods, which are SOP, BDD, and FM. And here SOP is an exact method, and BDD and FM are heuristics for this problem. And what we are showing here are the runtimes that we obtained. So what we can see is that we are much faster than the exact method, but we are even comparable to the heuristics, although opposed to the heuristics we do have the quality guarantees, so we can control how far away our solution is from the optimal solution. But much more important than this is that due to the polynomial runtime of our algorithm, we were able to solve this problem for functions with up to 100 million input bits, whereas to the best of our knowledge, the previous exact methods worked for functions with at most 200 input bits, and even the heuristics worked not for functions with more than 1000 input bits. And another advantage of the method that we propose is that we actually do not need to have the function given in any particular form, so we don't need to see the whole truth table or some logic representation of the function. So to conclude, we have introduced a probabilistic approach to the embedding problem which is an NP-hard problem. And our probabilistic approach, our method runs in polynomial time, so polynomial in the size of the input function. And we have controllable quality of solutions, so we can control how far away from the exact solution we are. For more details, please check out our paper. Thank you very much.